Right. Day 4, using operations with scientific notation. Moving to number 16. A company spends a total of $64,500,000 on salaries for its workers. If the company has 1.5 times 10 to the third power workers, what's the average salary per worker? So our total salary, they gave us our total salary. And they gave us the workers, the number of workers. So we really are just comparing the two, and we're just trying to find the amount per worker. So the dollars per worker. Okay, and 1.5 times 10 to the third. So the first thing we need to do is change this very large number from standard form to scientific notation. Okay, so we should have 6.45 times 10 to the 1, 2, 3, 4, 5, 6, 7th power over 1.5 times 10 to the third. The same thing we've been doing is we've been breaking apart the coefficients and separating them from the powers of 10, and we're going to do the exact same thing here. So we'll do 6.45 divided by 1.5 times 10 to the 7th divided by 10 to the third. So 6.45 divided by 1.5. Oh, I'm actually going to make sure that my divisor is a whole number so I don't have to get all confused about decimal points. So I'll need to just move my decimal place once to the right on my numerator and denominator. So I have 64.5 divided by 15. Pull up my decimal and just go ahead and divide like normal. 15 doesn't go into 6, but it does go into 60 4 times. Bring down my 5, and 15 goes into 45 exactly 3 times. So I have 4.3 times, and then 10 to the 7 divided by 10 to the third. That is my quotient rule for exponents. And all I need to do is keep my base the same and subtract my exponents. 7 minus 3 is 4. And this is written in scientific notation, so it's perfectly fine. But since we can definitely leave it like that. So it's this much money per worker on average. But if you want to actually know what that number is, all you'll do is have your 4.3, move your decimal place 4 places to the right. 1, 2, 3, 4. Add your placeholders. So each worker is making about $43,000 in salary a year. And this is what I would accept. This is what I really want is in scientific notation, but you need to also understand in the real world, this is what it means. Okay. And that's it for number 16. Moving on to number 17. Don't make too much fun of me because I know I'm going to mispronounce this. Stalactites, I think, are cone-shaped formations that hang from the ceilings of underground caverns. Stalactites can grow at a rate of about 0.005 inch per year. At this rate, what's the length of a stalactite that grows for 7.5 times 10 or to the times 10 to the 4th power years? All right, they grow at this rate per year. Oops. They grow at this rate per year, and this is the amount of years. So all we're doing is just multiplying these two. So we're multiplying 0.005 times 7.5 times 10 to the 4th power. All right, what we want to do is change our first term to scientific notation. So we'll have 5 times 10 to the, this 5 is much bigger than 0.005. And to get back from 5 to 0.005 is I have my decimal and I'll need to move it 1, 2, 3 places to the left. And since I moved it to the left, that's a -3. Okay, so now I have my 2 factors written in scientific notation. And I'm going to use my associative property to regroup. So I'll combine my coefficients together and my powers of 10 together. All right, so I'm going to go ahead and do 7.5 times 5. All right, so 37.5 times, and then I'm just going to use my product rule to multiply these, and I've got 10 to the first power. And this is super easy. Where all you need to do is you could either realize that this means that it's going to be 3.75 times 10 to the second power, or you can just simplify this to be 375. And if I need to write it in scientific notation, you know your coefficient needs to be a number between 1 and 10. And to get back from 3.75 to 375, you move your decimal twice to the right, and that's 10 to the second power. All right, so we have our answer here. That's the length of the stalactite after 7.5 times 10 to the fourth power years. All right, and we move on to our last one for day 4, number 18. The volume of the planet Venus is about 928 trillion cubic kilometers. The volume of the planet Mercury is about 6.08 times 10 to the 10th power cubic kilometers. What's the combined volume of Mercury and Venus? When they say combined, that lets us know we need to add them together. We're just finding the sum. So what we need to do is we can either choose to write both of the volumes of these two planets in standard form or in scientific notation. We've been rocking with scientific notation, so that's what I'm going to stick with. So Venus is 9.28 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. To the 11th power. And Mercury, they already gave it to us, is 6.08 times 10 to the 10th power. And we learned in this lesson that when you're just adding or subtracting them, you need to have a common factor. So all we'll do is identify the power of 10, that's the lowest, and that's 10 to the 10th power. So I need to change Venus to an equivalent expression that also has 10 to the 10th power. And that's going to be here, 9.28 times 10 to the first times 10 to the 10th. And I'll go ahead and regroup those, and that becomes 92.8 times 10 to the 10th plus 6.08 times 10 to the 10th. All I'm going to do now is keep my 10 to the 10th the same, and I'm going to add these here. So I've got 98.88 times 10 to the 10th, but I know that's not written in scientific notation, so I'll need to add an extra digit behind my decimal. So I'll have 9.888 times 10 to the 11th power is my final solution. And that is C. Maya chose D. What did she do? How do you think that she got that answer? So what Maya probably did is she probably divided those. I don't know why she would have done that, but maybe she did that. Let me make sure. And she did. So what Maya did is she divided 9.28 and 6.08. And she got about 1.526, which is very close. I'm not sure where the 10 to the 12th power came from, but yeah, I can see where she kind of got her coefficient from though. All right, and that is it for day 4. All right, great job.